Okay, so we're going to talk about Chapter 6 in your digital radiography and PACS. So your Carter book. Chapter 6 is covering the CCD and the CMOS. So within this chapter, you have some objectives that you're going to need to be able to answer so that you can do well on your exam. So go ahead and read those. Make sure you know these key terms and what they mean. Be able to define them, so flashcards is probably a good way to go. So we'll start off with our charge coupled device. So it's the oldest direct conversion digital radiography system used to acquire any digital image. So X-ray photons interact with the scintillation material, and the signal is transmitted by lenses or fiber optics to the CCD. During the transmission process, the lenses reduce the size of the projected visible image and transfer the image to one or more small capacitors that convert the light to electrical signals. So what happens here is that the lenses take the size of the image, shrink it down, and to the size of the projected visible light, and the image within those, the small capacitors, store it and convert the light to an electrical charge. So this charge is stored in a sequential pattern and is released line by line, sent to the analog digital converter. So a CCD is made up of photosensitive receptors and electronics embedded in a substrate material in a silicone chip. Okay, so I'll show you pictures of it here soon. Incident light from a scintillator strikes the detector, and electron-hole pairs are produced in the silicon. Now, a lot of this you'll be able to understand once you watch the ASRT video. This should help you understand what I'm talking about. The amount of electron-hole pairs is related to the amount of light that is absorbed. So they're directly related. The electrons are held by electrostatic forces in the array until the charge is read out to form the image. So this kind of gives you an idea. You can remember from the video exactly how all of that works. The chip is made up of a polysilicon layer, a silicon dioxide layer, and a silicon substrate layer. So the polysilicon layer is coated with a photosensitive material and contains the electron gates. So the silicon dioxide layer is the insulator, and the silicon substrate contains the charge storage area. So here's all the layers of your CCD, and you can just take a look. Here's your carbon plate with your chassis. You've got your light shielding unit, your scintillator, your power mode, and you've got your CCD sensors here, which we're going to take a look at here in just a minute, and your main substrate. Okay, and here you can see the layout of how it's all tied together for each one. So the detector element, or the DEL, we talked about this last week, contains 3 electrodes that hold the electrons in an electrical potential well. So it's kind of sitting in this little gully. The DELs are formed by voltage gates that at readout are open and closed like gates that flow electrons. So the gates they collect the charge on the silicon chips. The voltage sign is changed on the electrodes with each DEL, moving the electrons row down and the columns until each row is reached. So it goes a row and keeps going throughout the whole unit. This is known as the bucket, brigade scheme. So here is your typical, so you've got your storage capacitor there and your TFT, and you can see the rows and the columns here. So you have active drivers and glass substrate there, and your ADC converter. So here is another picture of it, just a piece of it right there. So you have your storage capacitor, your thin film transistor, your TFT, and your capture element is in the middle, so the well. So same thing there. So when the readout row is reached, Data are sent sequentially to this sense amplifier and are digitized. So the readout process requires that the movement of the electrons is limited, so multiple voltages changes occur very quickly to control that. So overfill of the dells will cause a blooming effect. So it's when excess electrons spill out of the dell and into the adjacent dell. So there's overflow drains are built into the array to reduce or prevent this effect. So when we look at these, you can see that there's space in between, and the area there around it is to protect it from overflow or your blooming effect. Okay, so it is not practical to manufacture a CCD chip larger than 5x5, so most ranges are between 2 and 4. The image must be matched to the size of the charge coupled device. So the CCD technology uses lenses that are fiber optics so that the image matches the receptor size. Reducing the image size involves several components that contribute to the quality of the image. So it's the scintillator, the light collection component, and the noise. The scintillator and the way it is constructed will determine 1, how many incident electrons are absorbed, 2, how light is produced, and 3, the wavelength or color of the light. So with the scintillator, there are 2 main types of phosphors. They're structured and unstructured, or turbid. So the cesium iodine is considered structured because of its needle-like crystals, what we talked about last week. So these crystals focus light into a very narrow area, reducing light spread, and allows us to use thicker scintillators, minimizing the loss of spatial resolution, which is the key. We want high spatial resolution. With the gadolinium oxysulfide, it's considered unstructured or turbid because of its powder-like grains. So the turbid phosphor produce more light spread, resulting in a decreased efficiency of the detector. All right, so lenses and fiber optics. So the optics of the CCD are critical contributors to the quality of the digital image. So lenses or fiber optics focus light into the CCD chip. The efficiency of the transportation of light to the chip is important because that's where the noise is created. The more light that is sent to the chip without creation of noise, the more efficient the system is, and that's the goal. The design of the optics is also crucial in imaging performance. So issues arise with geometric distortion, such as light scattering or lenses or optic flaws. So we'll talk more about that later on. So this gives you an idea. Here's your array. Here's your fiber optic tapers. Okay, so when we're looking here at your defective quantum efficiency, you're going to have to read this a couple times to make sure you fully understand it. So, defective quantum efficiency. The amount of electrons produced relative to the incident light from the scintillator is the quantum efficiency of the CCD. The quantum efficiency represents the absolute efficiency of the light collection and the signal created in the chip. So your quantum efficiency affects your defective quantum efficiency. Don't get those mixed up. The DQE, which is your defective quantum efficiency, is a ratio of the output signal to the signal to noise ratio. So a CCD is built to be as efficient as possible. So yes, we try to make it as efficient as possible, but you're going to learn here that it's really not as efficient as some of the other options. The polysilicon layer must be transparent enough so that light passes through into a deeper substrate storage area, but not so deep that it can't be captured into the potential well. So the spectrum sensitivity must match the spectral output of the phosphor. Less sensitive of the CCD to the light spectrum of the scintillator, the less efficient of the CCD. Several types of noise are associated with CCD technology. The most common are the statistical noise, dark or current noise, amplification noise. So, statistical noise is created by a lack of light photons from the scintillator. So, think of statistical noise as quantum model. If there are not enough photons striking the scintillator, or few photons are produced by the scintillator, then too few electrons will be generated at the output signal will be noisy, right? There's not enough light, it's going to be noisy. So dark or current noise occurs when the CCD chip operates without radiation stimulation. So when temperatures rise up too high and the electrons are moved into the bulk silicon layer or depletion area. At readout, unnecessary information is added to the image. Some manufacturers add thermoelectric cooling devices that drop the temperature as much as 40 degrees cooler than the room. So dark noise can be as much as 10,000 electrons per pixel per second. A 40-degree Fahrenheit drop can reduce the noise by a factor of 100. So temperature is very important when we're dealing with the CCDs. Amplification noise is common in digital systems, and there are no CCDs without it. All of them have it. The response of each CCD chip will vary across the array. Some pixels may not work. Software is used to correct the statistical variation caused by inoperable pixels. It takes an average of all the ones around it. So the more bad pixels, the worse the detector efficiency. But it's also the cheaper the CCD. So you found a real good deal, you're going to lose your quality. So as you can see here with film screen, we're not very efficient. And as we come over to the CCD and compared to the amorphous silicone that we use in mammography, you can see how efficient it is with our spatial resolution. Okay, so CCD applications. They're used in several applications in radiology, so digital fluoroscopy, stereotactic breast biopsy, digital mammo, and general radiography. So with digital fluoro, the CCD is a great replacement for the TV pickup tube. In the image intensifier, you'll learn about this next year. The CCD size is 2 to 5 centimeters, which is close to the same size as the 1-inch output phosphor of the image intensifier, so it's a great option. The CCD readout is linear and has a greater dynamic range than the TV tube. Oversaturation is almost 0, so blooming is greatly reduced. Shorten the recovery time from one image to another is the benefit of that. CCDs are more compact than TV tubes. Oh yes, I would agree with that. CCDs are not susceptible to electron scanning errors, which is very nice. A single detector can be used because of the typical field size of 50 by 50. This is stereotactic. Most current systems use a 2.5 by 2.5 centimeter chip. It results in some demagnification. So what is demagnification? It's the process of reducing the phosphor output image to the size of the active area on the CCD chip. So lenses, optics, and mirrors are used in this process. Noise is not as much as a factor because of the low dose. Newer digital mammography systems are replacing CCD with flat panel technology. All right, so in general radiography, CCDs may be tiled to a 16 by 12 array to a single CCD. So cesium iodide is the common scintillator material. Whole body scanners used in trauma and forensic pathology applications. So 12 CCD cameras are coupled to gadolinium sulfur oxide scintillators with tapered fiber optics, which I showed you a picture of that. The tube and the receptor array are housed in a C-arm type of mount, and a fan beam or slot scanning device moves down the length of the table or the stretcher. The scan can be any length up to 180 cm. So this is a picture here. You can see the TFTs and how it goes into a pixel image. So CCD advantages and disadvantages. Advantages of CCDs are simple and modular, easy to repair, replace, or upgrade. CCDs are relatively cheaper than TFTs based flat panel systems. And the disadvantages is the demagnification issues and reduced DQE. So complementary metal, oxide, silicone, CMOS. Systems are developed by NASA. They use a scintillator, so when they're struck with X-ray photons, they convert the light into the X-rays into light photons and store them in capacitors. Each pixel has its own amplifier, switched on and off by circuitry with the pixel, converting the light photons into electrical charges. Voltage from the amplifier is converted to an ADC, also localed in a pixel. The system is highly efficient and takes up less field space than CCDs. And this is what it looks like. And I'm going to stop there and we're going to pick up on the next. You only have a few more slides, but it's important that you know it. So we'll pick up from the slide in your next PowerPoint.